I found over the years for most folks, when you are in the section that's dealing with a particular type of series or series test, it's pretty easy to get into a rhythm and be like, oh, let's just do this or let's just do that. Let's identify what's going on. But when things are out of context, that's when the struggle happens, right? So let's kind of take this out of context. I want to continue to give you that framework from which you can operate, whether something feels in or out of context. And so the first thing that I always consider, and I don't think we've quite gotten all the way there yet, the first thing I always consider is the nth term test. And I say haven't quite gotten all the way there yet, is I would like to just try to do this mentally. So let me show you what I would hope you would do in your brain. We start off with this and we say limit, let's try that again. There we go. Limit as n goes to infinity of 1 over n to the 4 thirds. And we think about what that equals. So I would want you to at least consider this up here in your brain. So what do you think? 0, right? Because the denominator is getting huge. The numerator is held constant at 1. So the whole thing is headed towards 0. So what does the nth term tell us? Nothing. The nth term tells us absolutely nothing. All it really says is move on and do something else. Right? Do something a little more advanced because I'm not going to tell you anything. In what scenario would the nth term test tell us something? Okay, infinity. What other scenario? Any other number besides 0? So maybe I could put this. If we get this, something other than 0, what's the conclusion we can immediately jump to? Diverges, right? Because at the end, you're going to be adding that number on infinitely, and so you're going to get a diverging sum, and you could just stop right there. So that's why I say you want to consider this, because sometimes you'll get a divergent series based on that, and you could just stop right there, and the whole question took you like 20 seconds instead of doing all this other stuff first. So at least mentally consider that. Here, it was absolutely no help. Okay, so the next thing maybe we ask ourselves is, all right, nth term test didn't help at all. What about the geometric series test? Because that one was pretty good, because with geometric series tests, all you have to do is think about what R is. Once you figure out what R is, you can make a pretty quick conclusion, right? So we could think about that here, but that means that the series has to be a geometric series. So is this a geometric series?
No.
It's not. Why not?
Because if not, then it's already to the end as n total.
Yeah, that's right. So if the base is a number and the exponent is a variable, it's geometric. If it's the other way around, it's not geometric. And so geometric is very useful and it's pretty easy to use, but it only works for geometric series. And so it's kind of limited in that perspective, right? It can only work with that type of series. So it's not geometric series. Okay, so let's think about all the other ones we've got. We've got some tools we have in our toolbox would be like the integral test, the p-series test, as well as is it harmonic. So of those three, those are all kind of lumped into that same chapter we've been working on. Is it a p-series? It is a p-series, right? Because a p-series will always look like this. Sigma from n equals, whatever to infinity of 1 over n to the p, where p is a power, and this perfectly fits it. Now, if this was 1 over n to the 4 thirds plus 1,
No.
it's not a p-series anymore. So when I say a p-series is 1 over n to the p, I mean exactly that. No plus ones, no minus ones, no plus or minus anything else's. It's just going to be 1 over a single base with an exponent, and that's it. That make sense? Yes, ma'am.
With the p-series, is there a way to find out what number it converges to?
Sometimes. Probably most of the time. Most of like the typical ones, like say 1 over n squared. We'll talk about that in a second. It's interesting what they converge to. Let's see. I think I know what it is. Sigma. I think it's if you go from 1 to infinity of 1 over n squared. I think it ends up being pi squared over 6. If I remember correctly. There's all kind. Yeah, and so. When you say, okay, that's cool and everything, so how do we get from the left to right? How do we get from point A to point B? That's a whole other question. Much, much, much more involved. So finding the sums of these series can be hugely difficult to prove. And like I said last time, for some folks, like that's their doctoral thesis in the past has been proved that this series actually adds up to be whatever. So it's not simple in the slightest. So anyway, but many of them have been calculated. Okay, so since this is a p-series, then we can use the p-test on it. So what is the p-value for this particular series? 4/3. Okay, so p is equal to 4/3. What does that tell us? It converges. Okay, so we want to write down the key relationship, right? What does the p-value have to be in order for the series to converge? Just greater than 1. Okay, so we can say p equals 4/3, therefore p is greater than 1. Obviously 4/3 is bigger than 1. So we can say, therefore, by the p-test, our series converges. And that's it. What do you think? So each time we've done one of these, I've tried to take it all the way back to the beginning. What you guys will find later on is I've got a flow chart for you as far as your flow of thought, and I'm trying to build that up as we go. Okay, so what I want to do right now is made some kind of a judgment. Yes, it is geometric. No, it's not. If it was, we could use a geometric series test. If it wasn't geometric series, then we said, well, could we use the p-test on it? Could we use the integral test, the harmonic series? Kind of ask that series of questions. And I was really narrow, right? Wasn't I really narrow with my definition for the p-test? Remember how I said the p-test, it specifically has to be sigma of 1 over n to the p, right? So if you have 1 over n to the p plus 7, not a p-test anymore, right? So it's a very narrow definition, and so you got to figure if that's a very narrow definition, doesn't that mean that there are a lot of other series that don't fit that definition, right? And so these comparison tests that we'll take a look at here would be tests that would help us with many of the other functions that you might see. So I would say the comparison tests can be very, very broad. They can handle a lot of different things. So the comparison test literally is what you think it is. We're going to compare, right? We're going to have one function, we're going to compare it to another one, and we're going to use that comparison to decide what happens with our original series. Really, it's going to require us to pick a good comparison, and good is in quotations there because who knows what that means at this point. It can mean lots of different stuff. But let's kind of focus on the nuts and bolts of the comparison test, and then we'll do some examples. So the presupposition here is that 0 is less than a sub n, which is less than or equal to b sub n. So on a graph, what I would say then is that a sub n and b sub n are always what?
Positive.
Always positive. Both of them are always positive. And furthermore, b sub n is higher than a sub n, right? So it's pretty important that we realize that. So on a graph, I'll just sketch this out here roughly. So I'm going to say b sub n would be up here, and a sub n would be down there somewhere. At least on the interval that we care about, b sub n will be higher than a sub n. All right, so here we go. Here's how we do our comparison, all based on that. If the series for b sub n converges, then the series for a sub n also converges. Let's go all the way back to that chapter 8 stuff. Do you guys remember when we talked about those improper integrals, some of which converged, some of which diverged, some of which, remember how some of them looked really close to each other? For instance, I know I compared these. Integral from 1 to infinity of 1 over n. Well, we did x back then. And I compared it to integral from 1 to infinity of 1 over x squared dx. And if you guys remember, we actually got a real number answer for this, right? And for this, we got infinity, dne. So I remember asking you guys the question. It's like, wow, how could these two integrals, which really look similar, I mean, the only difference is the exponent on the first one is 1, the second one is a 2. Like, how could they have such radically different answers? How could one of them have a real number answer and the other one have an infinity answer, right? Do you remember what it was?
Because whenever it's like bigger than like just that exponent of 1 on the bottom, it converges fast enough to.
There it is. Fast enough, right? And so, and you're right, it does have to do, in this case, with the exponent, right? We could have approached this from a p-series perspective then, right? But it is that question, what Drew just said, of fast enough. So this series up above, 1 over x as x goes to infinity does approach 0. It just doesn't approach it fast enough. Versus this one here, 1 over x squared, does approach fast enough. And that we found out later that dividing line is when the exponent is 1. So along that line of thinking, if you think back to this comparison test now, and you say, well, if b sub n converges, doesn't that mean that b sub n approaches 0 fast enough? Right? And if b sub n approaches fast enough, and a sub n is always lower than it, doesn't that mean then by comparison that a sub n would also converge or get to 0 fast enough? Do you follow? Does that seem logical? If b sub n gets there fast enough, then a sub n being below it would have to get there even faster, right? Therefore, you could say, all right, well, if b sub n converges, then a sub n would also have to converge. So then the flip of this, I guess this would be the contrapositive, I think it is. If you use, I think that's what it is. The contrapositive would be true as well. So if the lower function gets there too slow, then wouldn't the higher function also have to get there too slowly? And so if a sub n diverges, then b sub n diverges as well. Okay. I hope that makes sense. Let's talk about what we cannot do with this. The converse is not true. So if I were to say something like a sub n converges, so the lower function converges, does b sub n converge? What do you think? If a sub n, which is the lower function, converges to a real number, does b sub n converge?
You can't tell.
We don't know. It might or it might not. We just cannot tell with the comparison test simply because of the vertical relationship. A being lower, it converges, that's great. It doesn't really tell us anything about b sub n converging. So if we find ourselves in this situation, what that means then is we picked a bad comparison. We need to pick a better comparison. Fair enough? Okay. So I'll say it again. The key is to find a function that fits that requirement and is something that you know about, right? Do you know the convergence? Do you know the divergence? And so stop and think for a second. The last thing is pretty key there. And has a known convergence or divergence. And so these are pretty limited. And we haven't talked about a whole lot of series yet. We've talked about geometric series. We've talked about harmonic. We've talked about p-series test and integral test. Just a handful of functions we've talked about. We're pretty limited. And so we have a pretty limited number of series we can compare to. So don't feel like there's just an insurmountable number of things to think about there. So let's do some examples, just a couple of them here, and we'll see how this turns out for us. Let's do this first one together, show you kind of what I'm getting at as far as how to compare. So let's analyze this. If you don't mind, let's start all the way at the back. At the very, very start, let's analyze this for, each test that we've talked about. So what does the nth term test tell us about number 1? Say again? It tells us nothing. You're right. Because if I do that, I'll erase this, but if we do the whole test, limit as n goes to infinity of 1 over 2 plus 3 to the n, we get 0, don't we? The 3 to the n is going to grow pretty large pretty quick. And so we will get 0 for the nth term test, which means nothing. Move on. So then we say, great, we got some other tests we can do. So let's think about the geometric series test. Is that a geometric series? You're going to be tempted to say yes, aren't you? because of this right here. 3 to the n. But doesn't the 2 mess it all up? The plus 2 messes it up. So it's not a geometric series. Remember, these are, like when we talk about p-series and geometric series, the definition is quite narrow. Right? It's not, throw some variation in there and it's all good. It's a pretty narrow definition. Okay, so it's not geometric series. How about, is it harmonic? No. Yeah, the 3 to the n kind of blows that out of the water. Integral test. The 2 kind of messes up the integral test. P-test. P-test requires that the exponent just be a number instead of a variable. So it's none of those, right? So if you logically followed everything we've done so far to its hopefully logical conclusion, at this point you have to be like, I don't know what to use. All the tools so far don't work. However, comparison is a very broad tool. It'll work in a lot of cases. So what we want to do is we want to stop and think for a second. What function is quite similar categorically to this one that we could use to compare? That the key is that we either already know or can pretty quickly determine the convergence or divergence of. What do you guys think? And this can be, I have no idea what you're going to say, but I want to hear what you want to say. 1 over 3 to the n. Okay, let's try it out. So if we use 1 over 3 to the n to compare, then how about this relationship? We have to set up this relationship right here. Where would the 1 over 3 to the n... Oh, I'm sorry, go ahead.
I was just wondering, why doesn't the integral test work?
So the integral test... let's explore. Integral from 1 to infinity of 1 over 2 plus 3 to the x dx. So the integral is integrand is a fraction, right? So with fractions, let's think about everything we can do with fractions. So the first thing I want you to consider is ln, is the derivative of the bottom and the top. Now the derivative of the bottom would be ln of 3 times 3 to the x. So it's not ln. Is it flip up? If you flip up, you're going to get 2 plus 3 to the x to the negative 1. Remember, whenever you have quantity to the negative 1, you're about to divide by 0, right? So it's not going to be flip up. Arctan or arcsine? It's not either one of those. Remember, arcsine has a square root, and it's a subtraction problem. And then arctangent is u prime a over a squared plus u squared. And the 3 to the x really messes that one up. If it was x to the third, we could probably make that one... Well, no, even still the numerator would be wrong. We still couldn't make it work. So this was none of those. And remember that we did the completing the square thing with those two?
Yeah.
That's not going to work, again, because of the 3 to the x, cuts that off pretty quick. And then we looked at one other fraction integrand, and that was when we did partial fractions, right? Partial fractions with 3 to the x, I don't know. I don't think it's going to work. So I guess what I would say is, even though this function is positive, right? Continuous, I agree, and decreasing, I would say, for the whole interval, since we either can't easily or even ever find the antiderivative, we leave the integral test alone.
Okay.
So it really comes down to, can we find the antiderivative or not? Because it fits all the other requirements, right?
Yeah.
Positive, continuous, decreasing.
This looks pretty good, but
Yeah, yeah. Just comes down to, can you actually execute the details? And I don't think we can.
Okay.
Good question. All right. If you have questions like that, you got to ask them. That's an excellent one. I'm happy to do that. Okay, so comparison. Let's go back to the comparison that was proposed by Hayden. I left you here. How does 1 over 3 to the n fit in this with the 1 over 2 plus 3 to the n? Which one's bigger or smaller? Is 2 plus 3 to the n, won't it always have a bigger denominator?
Yeah.
Which will make the whole fraction be just a little bit smaller. Okay, so I would say the correct relationship is, why do I keep doing that? Is this. 1 over 2 plus 3 to the n less than or equal to 1 over 3 to the n. So that's the correct relationship as far as the vertical positioning goes, the heights. Okay, so let's think this through. Hayden has given us something to compare. The question is it going to work, right? So the next thing, we have this relationship set up pretty well. Tell me about the convergence or divergence of our comparison series. Does it converge or not? Because we need to know. If we don't know, that's kind of a worthless comparison. Converges, why?
Because the coefficient is greater than 1,
Which coefficient?
like the 3.
Yeah, I agree 3 is bigger than 1, but that's not why. Let's back off a little bit further. What kind of a series is this? What did Hayden propose?
Geometric.
It's geometric, isn't it? We could rewrite it a little bit more advantageously, maybe like this. 1/3 to the n. And so based on that, remember the key feature of the geometric series is identifying the common ratio. Like the number that you multiply by to get the next term in the series. So what's the common ratio? 1/3. Okay, so I would say something like this. And I agree with you, Jared, that 1 over 3 to the n does converge. I'm going to say that converges, there we go, by the geometric series test because r equals 1/3 and 0 is less than 1/3, which is less than 1. So my common ratio is between 0 and 1. So if you've got a geometric series, common ratio between 0 and 1, then it converges. Okay? So what we found here is that with the comparison that Hayden chose, the function that we know to be higher, and let's put this in here too. Let's make sure we specify our interval. On the interval 1 to infinity, the interval could be problematic in the future. I think that it's for sure true here. So on our interval 1 to infinity, the comparison that Hayden shows is always higher than the series we care about, right? And furthermore, we just found out that the series that Hayden proposed converges. So can we draw a conclusion? I think we can. So we can say, therefore, by direct comparison, or you can say the comparison test, the series sigma from 1 to infinity of 1 over 2 plus 3 to the n also converges. So Hayden, you picked a really nice comparison. I think that's the best one, the easiest one, I guess. I'm sure there are many, many, many others, but I think that's the easiest one. If you wanted to look at a graph, you certainly could. Maybe, I don't know, maybe that's what Mackenzie did, but you could look at a graph of the two comparisons, or of the comparison versus our original two functions here. I think you'd find that from 1 to infinity, our 1 over 3 to the n is up there. And then the one that we wanted to compare would be down below it somewhere. And so based on that, since 1 over 3 to the n converges, we can say that our series also converges. All right, you getting the hang of this? Is this okay? Yeah, Tess.
Are you supposed to know that 1 over 3n is going to be higher than 1 over 2?
You're asking how would we know that?
Yeah.
So I think what I would do, like there's no way that I would ask you to plot every point to prove that. What I would say is this, and this is where I think the interval comes into play. If you think about the interval, we're going from 1 to infinity, right? So 1, 2, 3, 4, 5, dot, dot, dot. At every single point, I think, for every single n value, the denominator of 1 over 2 plus 3 to the n will always be 2 bigger, like literally the number 2 bigger than 1 over 3 to the n. And so since the denominator of 1 over 2 plus 3 to the n is always going to be a little bit bigger than 1 over 3 to the n, 1 over 3 to the n will always have a higher overall value by just a little bit. So I can't really... How are you supposed to prove that for every single n value, right? You're never going to finish. And so the idea would be for you to think through, okay, because we're talking about the relationship that I wrote right here, right? What we're talking about is maybe if you plot a few points whether literally on paper or mentally in your head, and see the pattern. You think, okay, no matter what I plug in, the denominator over here will always be 2 bigger than the other denominator. Therefore, oh, I get it. Like just making that statement right there is good enough, right? It's an important condition, right? And so you'd want to be able to, check that condition off the list. But as far as being able to conclusively prove it, I think a graph is a really nice way to do it. But otherwise you got to make a statement. Like if it said prove it, like if somebody said, hey, I need you to prove that, I would say what I just said. 2 plus 3 to the n is always bigger than 3 to the n on the interval 1 to infinity, because the denominator is always going to be 2 bigger, right? And therefore, since those are denominators, that'll cause the fraction on the left to always be a little bit smaller than the fraction on the right. I would just have to use logic and reasoning and deductions as opposed to numerical reasoning. Okay. Good question. Please ask more. What else? And by the way, so your quiz on Wednesday does not include this material, but in the spirit of just openness, if you were taking your quiz on Wednesday and you saw something and you thought, oh, I could totally use a comparison test. That's fine. Like the question will be, is it correct math? Not which section of the book did it come from. So unless I've otherwise specified, if I said, hey, use this test or use that test, if you want to use something like this, I'm okay with that. Maybe it won't always fit the best, but if that's what you choose to do, I'm okay with that. So anyway, just food for thought there. Anybody else? Okay, so we've only got a short amount of time left, but what I thought we could do with number 2 here is kind of get us ready for tomorrow. I thought what we could do is determine or try to determine an appropriate comparison. So can I get some proposals from you, like anything? Say again?
1 over root n.
Okay, 1 over root n. We're just going to list out these proposals for comparisons, and we'll try to hash through these tomorrow. Anybody have a different proposal? Just maybe you just want to disagree with Will just for fun, or you think you actually do have a better idea? Clearly what Will has proposed is quite similar to what Hayden proposed, right? Do you think you have anything better? Do you think he's wrong? Do you think he's right? Whew. No alternatives. You just think he's right. Okay. So it's like having a presidential election with one name on the ballot. Punch the ticket or don't. He's going to be president. All right. So we're just going to leave it at that? No other contributions? Okay. So tomorrow, when I see you again, we will find out. Did you put all your faith in Will correctly, or was that a mistake? We shall find out. All right. Have a great day. See you guys.